EDX Mechanics 1, Mechanics Basic Principles, Equilibrium of Forces. We've previously seen Newton's first law, which states that a body moves with constant velocity in a line, or, as we're interested in here, will remain at rest if there is no net resultant force acting upon that object in any direction. So this first law explains the natural motion of a body, that it would normally go in a constant speed in a straight line, or as in this case it will remain at rest. The total force will equal zero if an object is in static equilibrium. Also, just a reminder about resolving forces into components. If we have a force F at angle theta, we can put that into components by doing a little bit of trigonometry. So this horizontal component of F, if we did some trigonometry on this right angle triangle, would be F cos theta, and the vertical side of this triangle, if we did some trigonometry, would be F sine theta. And although these two diagrams are equivalent, it's the diagram on the right that would be useful to us in a particular scenario. Notice the components are perpendicular to each other. So here we have a system which is in static equilibrium, and we want to find the values of P and Q. So I'm going to apply Newton's second law, and I'm going to apply it horizontally. I've decided that to the right will be my positive forces, so to the left will be my negative forces. So if we start off with a 10 Newton force, and imagine drawing a little triangle on that 10 Newton force, the horizontal side of that triangle, or the horizontal component, would be 10 cos 50. If we draw a triangle on this 7 Newton force, the horizontal component of this triangle would be 7 sine 70, and that would be pulling to the right, so that would be a positive component. P is perpendicular to the horizontal direction, so no horizontal component. Q is acting to the left, so that is a negative Q, and because we have static equilibrium, that total horizontal force must be 0. And if we rearrange for Q, we get Q is 13.0 newtons to 3 significant figures. I now need to find P, so I need a vertical method, and I've decided to take upwards as positive. So I'm doing Newton's second law. I'm going to take upwards as positive. So upward components are positive, downward components are negative. So if we start off with a 10 Newton again, so I want to know how much of that 10 Newtons is vertical. So if you imagine a little triangle, the vertical side of that triangle would be 10 sine 50, and that's acting upwards. I need to know how much of the 7 Newtons is acting vertically. So if you imagine a little triangle there, the vertical side of the triangle would be 7 cos 70 degrees. That would be acting straight down, so that's a negative component. P is acting straight down, so that's a negative force. Q is acting horizontally, so we don't need to it doesn't have a vertical component at all. So this total vertical force must add up to 0, and if we rearrange for P, we get P would need to be 5.27 newtons to 3 significant figures. So we found Q and P required for static equilibrium to exist. And there's a more detailed solution of the problem. So here we have a 6 kilogram box which is at rest on a rough plane. The plane's inclined at 10 degrees, and we need to find the frictional force and the normal reaction. So the block has a vertical weight acting straight down, which is 6 g newtons. Its at rest on a rough slope, so the block will have a tendency to slide downhill, so friction must be stopping that tendency. So friction will be acting up the slope, so there's F. It's in contact with the slope, so there's a contact force, a normal reaction force, R, and it's in equilibrium. Before we apply any methods, it's worth just putting a reference dotted line perpendicular to the slope and putting the 10 degrees in the correct place. So we have equilibrium, so I'm going to do Newton's second law, and because it is on an inclined plane, I'm going to take positive as up the slope. So I'm going to do Newton 2 up the slope on the box. So looking at the forces in turn, F is acting up the slope, so that's in my positive direction, so that's a positive F. R is perpendicular to the slope, so has no parallel component to the slope. However, 6G, if we draw a little triangle on here, this side of the triangle, which is parallel to the slope, is going to be 6G sine 10 degrees, and that would be acting down the hill. So that's a negative component, and that total force parallel to the slope must be 0 because the block is at rest. And if I solve this for F, I get F equals 10.2 newtons to 3 significant figures. I also need to find R, so I'm going to do Newton 2 perpendicular to the slope, and I'm going to take away from the slope as my positive perpendicular direction. So going through the forces in turn, we have R is acting perpendicular and away from the slope, so it's in my positive direction, that's a positive R. F is parallel to the slope, so has no perpendicular component. But if we look at the 6G, there's a component of 6G acting along this dotted line, and that side of the triangle would be 6G cos 10. 6G cos 10. That's acting into the slopes, so that's a negative component, and that total force must be 0 because of the equilibrium. Solving this for R gives me R equals 57.9 newtons to 3 significant figures. And there's a clear full solution of the method. In this problem we've got an 8 kilogram mass and it's hanging from 2 light strings. If it's hanging from 2 light strings, then the tensions need to be labelled separately. So there's a pulling force in this string, which I'm going to call T1, and there's a pulling force in this string, which I'm going to label T2. There's the weight pulling straight down, which is 8 times gravity newtons, and we want to find the tension in each of the strings. So there are 3 methods. The first traditional method is to carry on using Newton's second law. So one approach is to do Newton 2, I'm going to take to the right as positive. So how much of this T2 is pulling horizontally? Well, if we imagine a little triangle here on the T2, the horizontal component would be T2 cos 25. So that's pulling to the right, so it's positive. If I want the horizontal component of T1 pulling that way along that dotted line, that would be T1 cos 65, and that's pulling backwards, so that's a negative component, and that total horizontal force must be 0 because the mass is in equilibrium. I can also apply Newton's second law vertically. I'm going to take upwards as positive, I've decided. So starting with T2 again, how much of T2 is pulling straight up? Well, that would be the opposite side of the triangle if I drew one, so that would be T2 sine 25, that's straight up. How much of T1 is pulling straight up? That would also be the opposite side of the triangle, so that's T1 sine 65, that's also pulling up, so that's a positive component. but don't forget the 8G, which is pulling straight down, so that's a negative force, and that total force must add up to 0. So we've done our traditional methods, and now we are faced with simultaneous equations. So one approach to this would be to take equation 1 and rearrange for T2. So you get T2 is T1 cos 65 over cos 25. And if we now sub T2 into equation 2, and I'm going to put the 8G on the other side, and we could take T1 as a common factor, so we'd have T1 as a common factor, and then we would have cos 65 over cos 25, don't forget the sine 25. We'd also have sine 65, and I'm going to put the 8G on the other side, and if I solve this for T1, I'll get T1 equals 71 newtons to two significant figures, and if we sub T1 back into equation 1, we will get T2 is 33 newtons. So that's a very traditional approach. The simultaneous equations, however, are quite fiddly, but there are a couple of alternative methods. One alternative method is to realise, in this particular example, it won't always be the case, but there was actually a 90-degree angle between the T1 and T2, and therefore I could have taken Newton's second law along the direction of T1. So we'd have the whole of T1 acting in that direction, so there's T1, and if you look at the 8G, how much of 8G is acting along the dotted line? That would be 8G cos 25, and it's acting in the opposite direction. So we could have had T1 minus 8G cos 25 adding up to 0, and it gives me the quick, efficient way of finding T1. I could have also done Newton 2 in the direction of T2 to exploit this right angle, so that would have been a positive T2. How much of the 8G is acting in that direction of T2? That would have been 8G sine 25, and it would have been acting in the opposite direction. Notice T2 doesn't occur in this first method because of the right angle, and T1 doesn't appear in this second method because of the right angle. And again, it gives us a very quick, efficient way of finding T2. There is also a third method which is worth being aware of. It's called the vector triangle method. So the vector triangle method exploits the fact that we have three forces in equilibrium. It will only work if we are dealing with three forces. So we've got three forces. We've got T1, we've got T2, and we've got 8G. You need three forces and you need equilibrium. And the vector triangle method exploits the fact that forces are vectors, and therefore the total vector sum must be 0. So if we start off with the weight as a vector, so that would be a vertical line. There's my vector labelled 8G. So there's 8G. I now need to add on T2 because I want the total force. So I'm going to add on T2 at the end of here. There is T2 added on. Now I need to add on T1. So I'm adding on T1. I know the total force is 0. So when I add on T1, it must form a closed triangle. So there's T1 added on. I know that T1 and T2 are perpendicular. And I know the angle between T1 and 8G is 25 degrees. So all I've got to do now is to do some trigonometry. So now I can say things like sine 25 is opposite, which is T2, over hypotenuse, which is 8G. So I can very quickly get T2 is 8G sine 25, and T2 is therefore 33 newtons. If I do another piece of trigonometry, for example cos 25, I get cos 25 is adjacent, which is T1 over hypotenuse, which is 8g. Quick rearrange, I get T1 is 8g cos 25, and therefore T1 is 71 newtons. You can only use this vector triangle method if you have three forces in equilibrium. And if the triangle isn't right angled, you could always resort to the sine rule. So don't worry if the triangle isn't right angled, you can use the sine rule to find the necessary force. And that brings us to the end of mechanics basic principles.